All right, 3-4 concept guide, linear programming. What we did in section 3.3 in creating boundaries and finding intersections of those boundaries was set up for this new lesson. Linear programming. For linear programming, the inequalities are called the constraints. The intersection, where the shaded regions overlap, is called the feasible region. When it creates a polygonal region or shape, we say that the region is bounded. We use these constraints and feasible regions in linear programming to find the maximum or minimum values that a linear function has for the points in a feasible region. The maximum and minimum value of a related function always occurs at one of the vertices, or points of intersection, of a feasible region. All right, so all those words you just used there is what we'll be doing in the next example problem. All right, example 1, graph the following system of inequalities, name the coordinates of the vertices of the feasible region, find the maximum and minimum values for this region of the function. All right, so, sorry, Connor Smith interrupted me. The function f of xy equals 3x plus y, that's the function that we're going to use to find the maximum or minimum values, okay? We plug our vertices into that function. Oops, too much. All right, I was interrupted again. I'm sorry. All right, here we go. All right, so again, that function right there we'll use to find our maximum or minimum values, and we'll plug in our vertices. So let's look at the 3 lines we were given. All right, first I have x is greater than or equal to 1. It's a vertical solid line through 1 on the x-axis. Then I have y is greater than or equal to 0, a horizontal line going through 0 on the y-axis. Then for my third line, I'm going to put it in slope-intercept form. Subtract 2x, subtract 2x, and I'll have y is less than or equal to negative 2x plus 6. So my y-intercept is 6, my slope is negative 2, so I'm down 2, right 1, down 2, right 1, down 2, right 1. And again, I've got another solid line. All right, so as you can see right here, if I shaded, x is greater than, I shade to the right, y is greater than, I shade up, and then y is less than or equal to negative 2x plus 6, I'm going to shade below the line. That little triangle will be my bounded feasible region. It will have 3 vertices. Those pink points are the 3 vertices, the points of intersection. So that point of intersection is at 1, 4. That point of intersection is at 3, 0. That point of intersection is at 1, 0. Those are my 3 vertices. I'm going to take those 3 vertices and plug them into that function that was given at the beginning, 3x plus y. So if I plug that first vertex in, I would get 7. When I plug in the second vertex, 1, 0, that gives me 3. And when I plug in my third vertex in, I will get 9. So when I plug them in, I get 7, 3, and 9. Well, my maximum value is the biggest number, 9, at the point 3, 0. And my smallest number, the minimum, is 3 at the point 1, 0. So that's what we're doing in linear programming. All right. The next example problem is for an unbounded region. Okay, unbounded region. So, if you look at this example, neither or none of those three lines are in slope-intercept form. So, you can put them in slope-intercept form. What I actually did was negative a over b for that slope, and then plugged in 0 for my x to get the y-intercept at 0, 3. So my y-intercept's at 3, I'm down 2, right 1, down 2, right 1. I have my line. Again, you could put that line in slope-intercept form by subtracting 2x, that's perfect. Second line, shading. That's going to be y is greater than, so I shade above that line. My next line, negative a over b, would give me a positive 1/3. That's confusing because the x and y are flipped right there. So you got to be careful of that. You could have added x and divided by 3. That would have been perfectly fine. But I just did negative a over b, which gave me 1/3, and plug in 0 for x. That'd give me a y-intercept of 3. Plot that point, up 1, right 3, or down 1, left 3, either way. Again, another solid line. Then for my third line, again, that is y. That would be, if you put in slope-intercept form, that would be y is less than, so you shade below that line. Next, the third line, negative a over b would be negative 2 over 1. B would be 0, 10. So that's going to be off the graph. I'm going to add that in there. So from there, I'll be down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1. Have my line. Well, if I had subtracted 2x on that third line, that would give me y is less than. And so that would mean I would shade to the below that line, or to the left. So right here, as you can see, I have an unbounded feasible region. It just keeps going forever down, but I still have two vertices. I have a vertex at 0, 3. I have a vertex at 3, 4. Hold on, let me add those in. 0, 3. And 3, 4. Also, I'm going to add in these lines. If you'd put these lines in slope-intercept form, you'd have y is greater than or equal to negative 2x plus 3. Here you'd have y is less than or equal to 1/3 x plus 3. And the third line, you'd have y is less than or equal to negative 2x plus 10. All right. So, again, I was given a function at the beginning, 5x plus 4y. So I'm going to take my two vertices, I'm going to plug them into that function that was given at the beginning. That 0, 3 would give me 12. 3, 4 would give me 31. Well, this means I'm going to have a maximum of 31 at 3, 4 and a minimum that is non-existent. All right, the reason why that is non-existent is because these arrows, I'm going to mark this, these arrows right here go down forever, right? They just keep going down, so that shading just keeps going down forever and ever and ever and ever. and ever and ever and ever and ever and ever. All right, so the minimum is non-existent there. If it had been if we had shaded above that green line, there would be a minimum and not a maximum. Okay. All right, so that's all I got for that sheet. We'll work on some more problems in class tomorrow or 2 days from now, depending on whenever you watch this. Pretty quick little video. Hope you'll have a good Monday or Tuesday night. Thank you. Bye.